right, so I think today will be our third and last lecture about randomized algorithms. I feel like it's important to teach hash tables, seeing that that's all we use. But just to recap what we've done in randomized algorithms. Oh, and then Thursday is planned to be maybe one more amortized analysis to give us a little more practice as opposed to something brand new. So just to recap, these randomized algorithms lecture has sort of been one part, some analytical tools and one part algorithms. Some algorithms we've done include randomized min-cut, quick sort, quick select. And then last Thursday, we started using hash functions for the first time, particularly for this heavy hitters or frequency estimation problem in the streaming setting. Not only did we introduce hash functions, but we also use this thing called Markov's inequality, whereas in the first lecture, I was really interested in, what's the average of this or that. This last lecture was also introducing this idea of what are the odds of being very far from the average and trying to limit that. So today we'll talk about hash tables. The tools we'll use will include last time. We'll use universal hash functions and Markov's inequality. And we'll also discuss, some technical generalizations of these ideas. So I think the back end of this lecture will be a little bit heavier, but partly it's more semi-impressionistic. What do people who work on hash tables think about? What does this whole look like? But we'll start with a more modest or easier to analyze type of hash table, which is called hash tables with chaining. And in the remaining time, we'll talk about a different kind of hash table called linear probing, which is more likely to be the one you actually use under the hood, but it's a little bit harder to analyze. Okay. All right, so that's the game plan, to try to do hash tables as well as we can in what time we have left. Okay, so guess you guys have all been to this page a million times. I'm guessing, do all of you learn Python as your first language? Oh, no?
Java.
It's still Java? Okay. Sorry, I'm not that old. Okay. Well, Python's kind of interesting because it just provided dictionaries by default. And at some level, it never even it tells the newbie what's going on under the hood. They just explain this is how you use it. It's very easy to use, right? Key value and stuff like that. And in fact, last I checked, and maybe it depends on the implementation, but even their object system and stuff like that under the hood are just being implemented by dictionaries and basically duplicating dictionaries when you make a copy of an object. Okay, so anyway, and here would be the version of I guess, your guys' first language. So, Java has an interface for map. Java is very clear about this is an interface and there's different implementations of a map. You can do binaries. Well, we'll talk about some in a moment. But this has, you can choose your types for key and variable as long as the keys are, hashable or sortable depending on the implementation. Right? So these are sort of the bread and butter of modern programming. I feel like no matter how well thought out your big project and whatever amazingly detailed object-oriented system you first design, you just end up passing around a bunch of maps and dictionaries after a month. Anyway, as we all know, the basic operations, you want to insert the key value pair, you want to look up the value associated with the key, maybe you want to remove a key, replace a key value, stuff like that. Okay. And just very, I think as an interface, very, very easy to think about and work with. Okay. So an extremely special case of this dictionary problem is when the keys are a set of contiguous integers from 1 to n. That actually, in some sense, is often the case for us because whenever I'm giving you a static problem, like do something on a graph, you have plenty of time, for example, to re-index all the vertices 1 to n. So then, 10 refers to vertex 10 from then on. And here the clear solution is to use an array, right? So an array is really best possible. You just allocate n slots for your n values. You can look up a value right away. You're not using extra space. You use straight access and RAM. Okay, so arrays are great. But of course, the downside, as we sort of talked about when we were talking about array lists last time, is that if your keys are not static and they're changing, right, or if they're not contiguous, then you start to have some issues. Right, so, what happens to m plus 1? Oh, do we allocate a new array and stuff like that? So that would be not great. But actually, a more general instance of the problem, and really the bigger issue, is that the keys aren't necessarily so pre-organized for you, numbered 1 to n, in a lot of applications. What makes dictionaries, I think, so appealing is the lack of, you don't have to pre-plan anything. You just put in a key and you put in a value and you keep going. And that's really the appeal. So the more general setting, rather than having contiguous integers, we'll have n integers out of some set 1 to u, where u is just some really big number. I chose u to stand for universe. But you can think of like bit strings, right? So u might have length 2 to the 10 if you're looking at bit strings of length 10. Okay. So if you wanted to use your array solution for this more general sparse setting, you do technically have constant lookup, insertion, and deletion, right? But the real issue is that you need to allocate one space for every key that might occur, right? And if u is like, the set of all bit strings or something, then this is ridiculous. So that is that's the problem with arrays. So a different approach, we can use ideas from last week or ideas you guys already knew, is to use something like binary search trees, right? As long as the keys are sortable, which is most often the case. It could be alphabetic if it was strings. And the great thing about trees is that the space usage is basically ideal. You need big O of n space to hold n keys. And assuming that you do a little bit of data structures, you can get log n time for insertion, deletions, and stuff like that. You could use lazy rebuilding, or you can use 2-3 trees or whatever else. Okay, so that would be the other end of the spectrum, right? So we sort of have these two basic approaches to this dictionary problem. One is to use arrays, which has fantastic time, constant time, that's best possible, but the space is proportional to the range of possible keys rather than the keys you actually have. And in search trees have great space. They're going to use space proportional to the number of keys, but your time is going to look like log n, which is sometimes good, but still worse than arrays. Okay. So the question is, can we get the best of both worlds? Can I get something that's constant time and big O of n space? That would be ideal. I can't imagine doing much better. Okay, and the answer, you might have guessed already, is yes, but we're going to use randomization. Okay, so we'll do some randomization, but then we are going to be able to get constant time and constant space per item, at least an expectation. Okay. All right, so we're going to use hashing, which we've already done before. So what's the high level idea? You have, n keys out of your much bigger space. You allocate a smaller array, hopefully of size somewhat close to the number of keys, and you do some usually simple arithmetic function that maps keys treated as integers into this smaller set of integers, mod m. Okay? And assuming that the hash function itself is pretty easy to evaluate and doesn't create any overhead, this is quite ideal because basically instead of going to a particular location based on a key, you do a little math, then you go to a different location based on the key. Okay. And ultimately, you only need constant time to find things, at least to find a slot in the array. Okay. But the only issue, of course, is you're just kind of mapping a big space into a smaller space so you can have collisions. Okay, so we can have two keys that get mapped to the same slot in your smaller array. This is called a collision. Okay. And really the name of the game in this design space is what to do about collisions. Okay. All right, so there's many ways, and this is a whole, specialized field. So I'll just list some examples of ways to handle. Actually, maybe I can ask, what are some approaches you guys might think of towards just at a high level dealing with this issue of collisions? High level ideas are fine. Yeah.
Make a tree for the collisions. So if there's more than one with the same slot, just tree there.
Okay, this is make a secondary data structure. For some reason, the most common thing is just to make a linked list and hope your linked list isn't very big. But certainly one can also make a tree or even another hash table. Okay, but the point is, as cells accumulate more than a few elements, we'll use some secondary structure. Could be as simple as a linked list, or as involved as a balanced search tree, and that'll kind of do a secondary search there. Yeah.
No, we just put it in the next available slot.
Okay. This is the one that'll occupy most of our technical attention today. So this is called linear probing. Okay. So the suggestion was, so I have an element X and maybe it hashes into this first slot, and that's occupied. So I'll try the next one. Maybe that's filled. I'll try the next one, the next one. Okay, and you're hoping that you won't get too many collisions in a row, and that sooner rather than later you'll find an empty slot to insert your element. Lookup will be done the same way. You go to the spot and you start scanning until you find it, or you find an empty slot, and then you know it's not there. We'll talk about it in more detail in a moment, or halfway through the lecture. Any other ideas? Yeah.
Maybe we can add a little voice in like a noise in hash function, so that when we had a collision, we can alter that noise so that we get a different result.
Okay, so the direct suggestion was add noise, but I'll maybe generalize a little bit to kind of more hashing, more randomization or something. You can't change the hash function once you use it because you need to find the things you've already added. So we don't want to change existing, but I'll give you an example that I had set up. That's called, I'm only describing at a very high level, cuckoo hashing. But the idea is to use two hash functions. Okay. So for a particular element, you see if the first hash function is occupied or if the second hash function is occupied. If, say, both of them are, if one of them's not, then great, you put it there. If both of them are occupied and there's already someone in each of these slots, maybe look at this and see if this guy's alternative hash is empty or this guy's alternative hash is empty and try to kick it out and reinsert and stuff like that. Okay, so that's actually something people do. Okay. The lamest idea maybe, is just to make the array so big that hopefully there's no collisions. Okay, and there's some question of how big does the array need to be so that there's no collisions. that's actually on your PSO. Okay. And there's many more strategies. Okay. All right. So chaining is the one we'll warm up with. It's the easiest to analyze, and you get the sense of what's going on. And linear probing will be sort of the deep end, but hopefully I can communicate at least the main ideas at a high level. Okay. All right. So let's start with chaining. So I just want to quickly remind us that when doing these hash tables, we look at these limited classes of hash functions that are kind of have some technical definition. So last time we used universal hash functions. So here the idea was, okay, it might not be a completely random function, but for any two elements, the odds of them colliding should behave as if it was completely random. So if there was k slots down below, there should be a 1 over k chance. I guess above we have been using m instead of k, so sorry about that. Okay. All right, and that's given by basically ax plus b, but you have to do some modulo of prime. Okay. All right, so let's talk about this chaining approach of hash tables. I've tried my best to diagram it out. So, so just to be clear, up here is sort of our big space of size u, and our hash function will first compute some value modulo p, where p is a prime bigger than u, and then it'll just do modulo m to get down to the smaller space. Okay, so there's two modulos going on, one at a high level, the other at a lower level. Okay, and I'm not sure if it's very visible, but down in the bottom we have a linked list of all the elements that got hashed there. So if you're inserting something, you go to the cell and you add it to the bottom, you add it to the top of the list. If you're doing a lookup, you go to the cell, you scan the list. Okay. So your running time for any of these operations are going to be proportional to the list, really, of the cell that you're interested in. Okay. Constant plus that length. Okay, so let's analyze this, and I think that the analysis should be similar in spirit to last class when we did heavy hitters. We did something very similar. Okay, but let me say the claim slowly. So here I'm letting n be the number of keys, and m being the size of the array that you're holding in memory. So probably m is greater than or equal to n, but it doesn't have to be. So the claim is that if I already have like n keys in a table, for example, and I insert the n plus 1th key, the claim is that this key will take basically n over m in expectation. The 1 is there just in case n is much smaller than m, and you still have to pay at least a constant. Okay. So the claim is that the running time should take roughly n over m. And I think you guys might be able to at least guess at a high level why. So m is the number of slots in your array, n is the number of keys. As usual, I probably shouldn't have used the two letters that sound and look the same. Yeah.
You spread n out into m spaces.
Yeah, okay, so in principle, the idea is we're spreading, okay, so if everything was spread out perfectly on average, like, I don't know, if we just got very lucky, then there would be exactly like n over m per, okay, so that's sort of what's going on. But now if I want to do kind of a proper expected analysis and go through the bells and whistles on paper, how might I set this up? So at some level I'm inserting some element x, and I want to bound the number of elements that collided with it, because that'll be the length of the linked list. Okay, and I want to figure out kind of the expected length of the linked list, or expected number of elements colliding with this particular x. So how do we set it up? Yeah.
You have a random variable as the indicator as one if for every pair they collide.
Okay, so let's say that there's you're inserting a new key and there's already n keys in the table. So I'm going to write 1 if the ith key collides with, I guess, the new key, we'll say. Okay? And 0 otherwise. Okay. So our running time is going to be proportional to the number of collisions, because that'll give you the length of the linked list. Okay. Now we want to figure out the expected running time, so let's put expected values around both sides. Okay. And what would be my next step analytically? Yeah.
You can pull the summation.
Okay, perfect. So linearity of expectation. And now we just have to look at a particular other key and figure out the probability of it colliding. Because it's a universal hash function, this will be yeah, 1 over m, kind of proportional to the smaller space, which is n over m. Okay, so at some level, this is, maybe at high level, it's very clear. We just want to say that the average running time should be the average length of a list, which in our mind is n over m, and this is just articulating it. Okay, and then it's very clear where we invoke the universal hash function part, and then, as usual, the magical step is linearity of expectation. Okay. So all these, average type of analysis, linear of expectation makes life much easier. Okay. So using just, ax plus b kind of hash functions, you do kind of, maybe as you guys expected, get this proportional running time on average. Okay. All right, so that's it for chaining. It's pretty simple. So what do I want to say? Okay, so that's so much for chaining, and we're going to move now on to the linear probing part. And somewhere in the middle, I'll introduce the technical parts as well. Okay. So, all right, so. Okay, so linear probing. Okay, so what's going on? So chaining was particularly nice to analyze and stuff like that. But I guess, people who are interested in hash tables and interested in making very good hash tables are really, really interested in performance. And so people aren't necessarily excited about having a linked list and having to create all these pointers and stuff in a secondary table. And it's often preferable to do everything in arrays for real-world performance. Okay? And not have to create all this pointer jumping and stuff like that. So linear probing is sort of almost a natural generalization from that perspective. You can think of it even as inspired by chaining. But so the idea is that if I want to insert an element x, and I find that the array is already occupied, then I'll start looking for the next unoccupied cell, and I'll put X there instead. Okay, it's almost like chaining if you think of the linked list going down the array. But I think the very practical upside of this approach is the fact that you're just living in one array. So there's no overhead from creating additional pointers or anything like that. Scanning is very fast, right? Especially if you think about how caches work and stuff like that. Your computer loads up probably a segment of the array anyway. And so scanning down an array is extremely fast. Much faster than a generic, following a pointer somewhere across your computer. Okay. So this was a hash table approach that was implemented, and I think also this simpler, because it is simpler to implement. I mean, we take linked lists and pointers for granted, but on old computers, you didn't want to allocate lots of stuff, so arrays were particularly convenient. So this is an implementation approach that was very, very old, and one that people have been using, and it's been working really well long before we were able to analyze it. I'll explain more in a moment. Okay, so that's how you would insert. If you want to delete an element, such as X, you would, like before, go to where it's supposed to be. You don't find it there, and so you start scanning until you find it. Okay, you're going to delete it. But the issue is that you do create a hole, which could cause some confusion for future lookups and stuff like that. So what you'll do is you'll start scanning and you'll look for any element that could have gone there if it were rehashed, so to speak. So in particular, Y is actually in its right place, HY. Okay. So underneath I've labeled sort of the address. So Y is really supposed to be in that slot. Z, meanwhile, seemed to have been pushed over at some point earlier. Okay. So, if I were to reinsert Z, it would go into that unoccupied spot. Okay. So we kind of scan and we fill the holes, and maybe you have to fill another hole and fill another hole, and so on and so forth. But you fill holes so that the lookup will work as you would expect later. Okay. All right. So after deletion, for this example, Z will fill in the spot left open by X. Okay. So there's the high level ideas behind how insertion, deletion. I guess I omitted lookup, but that hopefully is clear. Okay, so the running time of all these operations are basically just going to depend on, a hash in X, and how many consecutive slots follow X. Okay. Sort of like a run of occupied cells. And so that's really the question we need to analyze, is how long are these runs going to be? Because that's basically going to be the running time of our algorithm. Okay. Including deletions when you fill in. You're filling in from other consecutive slots. And in particular, we're going to focus on the case where the size of the array is still proportional to the number of keys. I think the constant I have in the notes is like, let's say m is at least 8 times the number of keys, but just some constant bigger. So it's particularly for this setting, I want to try to show that the runs aren't so big on average. All right. Good. Okay, so there's a little bit of weirdness going on because where an element is supposed to get hashed is not actually where it ends up. So I'm going to use the following words very specifically. I'm going to say that X hashes to a particular cell AI if h of X is equal to I. Like that's where it's supposed to be with respect to the hash code. But that might not be where it ends up. So I'll say that X occupies a cell if actually that cell contains X. Okay, I'll try to be specific about how to use those words because half the battle is just distinguishing where it's supposed to be and where it ends up. Okay. And I guess I'll kind of refer to intervals. I'll refer to intervals in the array like A, comma B as all the entries from index A to index B. And then that also includes like situations you wrap around. So if B is less than A, that means that A is wrapping around to B. Okay. You can think of the hash table as more like a circle. Okay. All right. So that's important to establish. And the main kind of, I think, invariant that hopefully was clear in the description of the insertion and deletion is that for every key X, let's say that X occupies cell L, okay, we're always maintaining the invariant that all the cells between where it gets hashed and where the cell it occupies, they're all filled up. Because the deletions were otherwise trying to fill in the holes, and the insertions were put into the first hole. All right, so hopefully that makes sense. Okay, so let me give a little. This is a question that somehow has some historical significance. So, like I said, people had been using this data structure already before kind of people were analyzing algorithms. So Knuth analyzed this, the same guy who did law tech and other stuff, in 1964, where he showed that if you have an ideal hash function, so everything is totally random, then the expected length of each of these runs will be a constant. I think in some interview he said something like it's the first algorithm that he ever analyzed rigorously. In some sense, it's one of the first algorithms to ever be really analyzed because big O notation roughly didn't exist before this. Okay. Anyway, so for ideal hash functions, if the keys are really random, or the hashes of the keys, then you will get constant time performance. And that left open this question of, what happens with limited randomness? Can you use universal hash functions or something like that, an actual implementable hash function, and make this a real data structure? Okay. So it turns out we'll need something a little bit broader or more general than universal hash functions. Okay. So these are called k-wise independent hash functions. We're going to need a 5-wise independent hash function, but let me explain. Okay. So a hash function is said to be k-wise independent if for any k keys out of your universe, in any k particular values, that's a typo, righto, whatever. In the hash space, the smaller space, the probability of x1 being equal to that first particular value, x2 being set to the second particular value, the probability of that particular combination is the ideal one, which is 1 over m to the k. So it's saying that for all combinations of k keys, it's going to behave like an ideal hash function. It doesn't promise anything for k plus 1. So universal hash functions, just thinking about 2 keys, turns out to not quite be strong enough. We'll still have k as a constant, but we'll need slightly more independence, so to speak, slightly more randomness. It turns out that a generalization of our universal hash functions will give you ky is independent. So here, h of x maps to a0 plus a1x plus a2x squared, and so forth, where all those coefficients are selected uniformly at random from a large prime number field. Okay. I think the main takeaway is that, again, it's a relatively modest arithmetic function. Okay, so that those definitions are needed. So Knuth showed that if you have ideal hash functions, if you sort of have infinite-wise independence, then you get this constant. Many years later, Schmidt and Siegel showed that if you have log n-wise independent hash functions, so any log n keys act as if they were totally random, then you get a constant. Okay. And then more impressive, Pogorzelski showed that if you just have 5 wise independent hash functions, so in particular a constant, then you'll get that expected constant running time. And 5 is very practical. Amazingly, follow-up work showed that if you had a 4 wise independent hash function, that's not good enough. So if you had a 4 wise independent hash function, you plugged into this algorithm, you can find specific examples that'll kill it. Okay. All right, so that's what we're going to try to prove. We're going to try to prove as best we can that if you have a 5 wise independent hash function, you can get this constant time performance. Okay. That means it's sort of like ax plus b, except probably with 5 coefficients. Okay. All right, let's see what comes next. Okay, that's right. Okay, so that's our claim. If H is from a 5 wise independent hash family, then we'll get expected constant time for m, I guess here, greater than or equal to 8n, but you could probably play with 8, try to make it bigger, try to make it smaller. Okay. All right, so before we launch into analysis, I do need to finally introduce, and I was planning to omit the proof because it's a bit of calculations, this generalization of Markov's inequality that will take advantage of this 5 wise independent hash function. Okay. So first, sort of analogous to the definition of k wise independent hash functions, you can have k wise independent random variables. Okay. So these are a family of random variables, say x1 through xn, and they're said to be k wise independent if for any k of them, the probabilities of them being equal to a particular set of values were as if they were completely independent. Okay, so combinations of k random variables out of your family act as if they're independent. They're not necessarily fully independent. Okay, so if you have a 5 wise independent hash function, then that's sort of like saying the hash values are 5 wise independent random variables. Okay, so it's only slightly more general than that previous definition. Okay, so here then is sort of the one kind of gory quantitative lemma that we'll need that takes advantage of this k-wise independence. So I think rather than doing the full proof, what I'm going to do is just focus on the intuition, why it's useful, and why it's sort of also a reasonable example for a general style of thinking. So let me parse it. So let's say you have n random variables that, for simplicity, I'm saying are 0, 1 indicator variables. Okay, so they're like coin tosses. But they're not necessarily independent. I only promise that they're, actually shouldn't be k, it should be 4. 4 wise independent. And let's let mu denote their expected sum. Okay. And suppose this expected value is at least 1. Okay, so you're tossing a bunch of coins. Well, they're not necessarily independent. So, the expected total number of heads is at least 1. Okay, and all I promise is that they're 4-wise independent. They're not completely independent coin tosses. Okay. All right, then, let me read this slowly. For any alpha greater than 0, the probability that the sum exceeds the average by a 1 plus alpha factor is at most 4 over alpha to the 4th mu squared. Okay, so what's this thing? So let me give an example. If alpha was 1, okay, it's saying the probability that the sum is greater than 2 times the average is going to be 4 over mu squared. Okay, let me compare that to what you would get from Markov's inequality. Okay, so previously we used Markov's inequality, which is a little bit simpler than this, and in fact it's used in the proof of this. So Markov's inequality, which doesn't require this 4-wise independence, would tell you that the probability of being at least 2 times the average is, at most 1 over the average. Or no, it's 1 over 2. Okay, so that's what we used previously. The probability of being 2 times the average is at most 1 over 2, 50%. If I said greater than or equal to 10 times the average, it would be 1 over 10. Okay, and so compare that to 4 over mu squared. Okay, now if mu is very small, then actually 1/2 is better than 4 mu squared. But what happens when mu is big, right? Especially, this often happens in computer science when we are studying like lots of data, lots of variables, lots of keys, and situations where the lots of translates to large averages. Okay, so often in many applications, the average is very large. You have lots of random variables contributing to a very large average. Okay, so in that case, when mu is large, or mu is even sort of the dominant factor, like mu is proportional to n, then you're having something that's going down at a rate of 4 over mu squared, right? Like 4 over n squared or something like that. And actually gets smaller and smaller as the average gets bigger and bigger. Okay, so this is actually an example of what's called a concentration inequality, a law of large numbers. As the average gets bigger, the odds of you deviating from the average are going down and down and down. That's what this is saying. As mu gets bigger, the odds of this tail event of exceeding the expectation by more than a factor of 2, for example, is going down at a 1 over mu squared rate. You don't get that from Markov's inequality. Okay? And only mentioned at a high level, these law of large numbers where you have large averages, they're only useful if the variables that add up to the average aren't all the same and aren't too related to each other. So you need some independence type of assumptions. Okay, so a more famous example that we aren't doing in this class is something called Chernov's inequality. This is when all the xi's are completely independent, like you really do have n coin tosses. Okay. Here, what we're leveraging is just 4-wise independence, just not at all completely independent, but that's enough to get a much better bound than you'll get from Markov's inequality. Okay, so once you start assuming a little bit more independence, then things, law of large numbers type of dynamics start to kick in. Okay, so I'm sure you guys will run into this a lot in whatever ML machine learning class is coming up. All right, so that will indeed at some point later. Okay, now let's go back to analyzing the linear probing. Okay, so we've established some kind of inequality. It's mysterious, so it'll show up later. Now let's return to linear probing. Okay, so when we analyze the algorithm, we're going to focus on kind of maximum contiguous subsequences of the array. Okay, so I'll call this a run. So a run just means like it's as large as possible, as many filled up elements as possible. Okay, if I took it's going to be surrounded by blanks on both sides, and everything will be filled in. Okay, that'll be a run. And at some level, we're hoping not to have large runs, because large runs will kill our running time. All right, so here then is a setup for our analysis. I'm going to fix some key x that maybe I'm inserting or deleting. Let's just say insertion for the sake of discussion. And I'm going to let I be the index in an array that it's supposed to go to. Okay, so I will be the hash code of x. Okay. And then I'll use capital R to denote the particular run at x. Right, so it might be like that would be the run. Okay. Actually, maybe it wouldn't include x if x is being inserted. So at that time, the run is just all those occupied slots, okay, that contain where it gets hashed. And our goal is going to be to show that in expectation, the size of the run is some constant. Our running time will be bounded above by the size of the run that it gets hashed into. Okay, but it's sort of a tricky thing to analyze. Well, because obviously these runs have lots of interference from other elements that don't necessarily hash into the same spot as x, right? The issue could be elements that hash into spots after x. It could even be elements that hash into spots before x. If this was occupied, then maybe this would be bouncing around for a while, right? So they're just elements kind of nearby, so to speak, of x. Okay. All right, so that's our setup. R denotes is sort of this randomized subsequence that denotes the run that x lands in. And I want to show that in expectation, the length of this run is a constant. Okay, so I think this is the key idea to break down this analysis. And it's a well-known trick, doubling trick. It's sort of appeared to some extent with the array list. But dyadic intervals, actually, I'm not sure if dyadic is spelled D-Y-A. I should check. Anyway, okay, so dyadic intervals. So here is the index, lowercase I, where our element is getting hashed into. Okay? And what I'm doing is I'm kind of looking at the intervals that surround it, but only in powers of 2, or roughly doubling. Okay, so for I sub 4, I'm going to go out 2 to the 4, which is probably 16 slots to one side, and 2 to the 4 slots on the other side. And so that total length of 33 is what I'll call I sub 4. So it's centered where x was supposed to get hashed into, okay, and stuff like that. So it's roughly doubling in size as you go up, although there's a +1 that throws it off a little bit. Okay. But roughly doubling in size as you go up. Okay. All right, so the reason this is nice, why not all intervals? We'll see that later, but at some level, the nice thing about doing the doubling is that I'm going to reduce my analysis. At some level, we're going to analyze each of these intervals. But one thing to already point out is that one of these intervals, there's only log n of them because they're doubling in size. So by doing this sort of doubling trick, as opposed to, say, looking at all intervals that surround where the element was going to get hashed into, I actually only have to worry about fewer things. That'll become more clear at the end. Okay, so one motivation for this definition is that if my run has length less than 2 to the k, like 2 less than 16, then I always know that my run is contained in sort of this kth dyadic interval. So, because I know the run contains I, and I'm going out to at least 2 to the k on either side. Okay, so if the run has at most 2 to the k elements and includes the middle, then it's going to be contained in I sub k. Okay. I mean, yeah, I feel like the way I'm presenting it, it's a little bit cleaner in hindsight, but I think this is really the hard part because it's not even clear where to start the analysis of this linear probing. Okay. On the other hand, if I knew the length was at least 2 to the k minus 1, so let's say that my run had length 10 or something, so it's less than 2 to the 16, it's more than 2 to the 3, okay? Then of course, because it's a maximal set of contiguous sequences, if I look at the total number of elements that get hashed in, let alone they also occupy, but all the elements that get hashed into the run also occupy this run. Okay? And all elements that occupy the run. Okay. So in each run, the set of elements that are occupying the cells is equal to the set of elements that get hashed into the run because of this maximality. So consequently, if I knew that the run, which is a matter of which cells are occupied, has at least 10 elements, I know that there's also 10 elements that hash into those cells. There's a slight distinction. Okay? But the real thing is that if I combine these two observations together, the hard part, I think, is choosing the right definitions. But now that we have those, then, okay, the probability that R is within this power of 2, R is, say, between 8 and 16, is to have that, I have to have that at least 2 to the k minus 1 keys or items or whatever hash into that bigger power of 2 interval that surrounds it. Okay, it might seem a little subtle. Okay, so we're saying that the odds that R has between 8 and 16 keys is at most the odds that at least 8 keys hash into that bigger umbrella of 33 slots. Okay? And why is this important? It's because at some level I sub k is sort of fixed, right? There are these kind of prearranged intervals around I. Whereas R itself is sort of more of a complicated beast. Understanding R well might be more detailed. It's not clear how to analyze R directly. It's a little bit easier to analyze these fixed intervals. These intervals are sort of fixed ahead of time. Okay. All right. So now we want to analyze the probability that too many intervals or too many keys hash into one of our specially selected intervals. All right, so we can do something similar to what we did with chaining, where I'll make a random for every other key. I'll make a variable x sub I. X sub I is equal to 1 if the ith key hashes into this interval, this special canonical interval, and otherwise 0. Okay. So now we're looking at this event. What is the probability that the sum of xi's is at least 2 to the k minus 1. Okay. All right. So I'm just gradually massaging this thing into a form that becomes kind of more and more applicable to some of those stronger analytical tools. Okay. All right, so a 5-wise independent hash function. Okay, so here we're finally going to use the fact that our hash function is 5-wise independent, which hadn't shown up until now. Okay. Now in this setup, I've sort of fixed the hash code of the key x that I'm inserting. Right? So everything is conditional on h of x equal to I. Okay? So conditional on that, the remaining hash codes are still 4-wise independent. This is why we have a slight discrepancy between the 5-wise independent hash function, and we're going to end up using an inequality for 4-wise independent random variables. Okay, so any 5 values act as if they're totally random. So if I fix one of them, the remaining 4 still act as if they were totally random. Okay? So conditional on the hash of the particular key we're looking at, the remaining keys, their indicator variables will behave like 4-wise independent hash functions. All right. Okay, so I want to use that inequality where I want to show, okay, the odds of having a lot of keys, much more than expectation, is small, particularly since we're doing a sum of 4-wise independent random variables. Okay. So the first step then is to try to figure out what is the expected number of keys in this interval. Okay. So, okay. All right, so what is the expected value of the sum of xi's? What is the expected number of items hashed into this interval? Okay. So, at some level, okay, the first step, as always, is to apply linear to expectation. Okay. And ask for each key, okay, what are the odds that it falls into this interval? Okay. And they're all going to be the same. So I'll have n times, okay? And so, okay, so first of all, it's going to be basically the size of the interval divided by the total size of our array, right? So the interval has size 33, the array has size 1,000. There's a 33 out of 1,000 chance that a particular key will land in the interval. Okay. So if I remember correctly, we have I sub k had size 2 to the k plus 1 minus 1, and m was set to at least 8n. Okay. So that expected value is at most n times 2 to the k plus 1. I'll just leave it like that. 2 to the 3 n. Okay. Some things cancel out. Okay, I think that's correct. Okay, so whatever, the number of elements that fall into this interval is at most 2 to the k minus 2. Okay. This will probably be the most kind of technical thing we do in this class. Okay, so the expected sum was 2 to the k minus 2. Hopefully the calculations will work out. And here then is where we're going to try to use our concentration inequality, where having a 4 or 5-wise independent hash function, leaving 4-wise independent indicator variables, is going to help us. Okay. So, all right, so I'm not sure if you can see, but on the right, I tried to put all the info up there. Maybe it's too small to be useful. But I want to write it in the form 1 plus alpha mu. Okay. So if I write that to be mu, then I guess we have 8 mu, if I'm not mistaken. Oh no, it's just 2 mu. Right? Okay. Right? So this thing is at most 4 over mu squared. Okay. And for us, mu is quite small. So you get 2 to the 2k minus 4, hopefully. Okay. So this will be something like 32 over 2 to the 2k. I could have easily messed that up. Okay. All right, so you get this bound. And what's the most important thing about this bound, which will be made clear in a moment, is that this probability of something bad happening on that case canonical interval is inversely proportional to 2 to the k. Okay? Which is roughly the size of that interval squared. Okay, so it goes down very fast. At some level, I'm not so concerned about very small intervals. Interval of size 10, okay, I have a run of size 10. No harm. But I am worried about runs that are size n, close to n or something, right? And if it's close to n, this is like 1 over n squared. Okay, so the bigger the interval that I'm worried about, the probability goes down rapidly. Okay. That's the most important thing. At a high level, we want a little bit of extra independence to use some law of large numbers because I'm really worried about the large runs in particular. Okay, so, all right, so what do we show? This thing is at most. I guess I can just write 32. It's not so bad. Okay. I thought I wouldn't have time, but I think we're going to be fine. Okay. So, we're almost done then. So the expected running time, okay, is equal to the expected size of the run up to constants. Okay. And then next we just have the definition of expected value. So okay, that's 1 times the probability the run has size 1 plus 2 times the probability the run has size 2 plus 3 times the probability. Okay. All right, so now here comes the nice part. At some level, if I try to address all n terms directly, you won't get a good enough bound. So here we're going to use the doubling trick, so to speak. It's the only example we'll see in this class, but it's good to know that trying to do tricks like this is really important for pulling off some of these more sophisticated analyses. So I'm summing up from 1 to log n. Okay. And what I'm kind of doing is I'm basically bucketing. So I'm saying, okay, what is the probability that the size of the run is between these two values? Okay, maybe I should start at 0 or something. Okay, so instead of looking at all the probabilities individually, I'm kind of grouping them up in powers of 2, right? So It's saying, like, okay, let's take 16 times the probability that the length of the run is between 8 and 16, plus 32 times the probability that the length of the run is between 32 and 64, and so forth. Okay, so I've taken this expected value and I've sort of rounded up to the next power of 2 and bucketed. So that's why you get a less than equal. It's only being conservative. But analytically, what's happening is that I have much fewer terms that are going to add up in the following. Okay, so if we now use this bound that we proved above, this will be at most 32, some constant. Okay, 2 to the L times 1 over 2 to the 2L. Okay, so the key point is that, again, that probability was going down very fast in L. Okay? So you guys will get to have the final word. So let me just do some canceling out. I'm going to cancel out one pair of 2 to the L's. Okay? So it's the sum of 1 over 2 to the L, where L goes from 0 to log n or something. Okay? Now finally, how do I deal with this sum? Yeah.
It's the sum of a bunch of values less than 1. So it should
Yeah.
be constant.
Perfect. So it's our favorite 1 plus 1/2 plus 1/4 plus 1/8 plus whatever. So it all adds up to 1 or 2 depending on whether you start at 0 or 1. So, okay, I guess in our analysis, this is at most 64. Okay? All right, so something magical has happened, but we're ultimately able to show that the expected length of the run is at most a constant. Okay? We did m was equal to 8n. If you made m bigger, this constant will go down. Also, if you're more careful about the analysis, you could probably push the constant down. I let the constant be a little bigger, but make the analysis a little bit cleaner because we're just having a discussion. Okay, so that is how you prove that linear probing works. I understand it's a little bit more technical, so it's sort of intended to be partly impressionistic and convey some high-level ideas, such as how do people actually design and analyze, really high-performance hash tables, introduce some of these ideas of why independence can help you, limited independence can help you more than not having any independence, right? Because we sort of went from a weaker universal hash function to a slightly stronger 5-wise independent hash functions, and then we get this very nice thing. So these are all, very nice big ideas that appear elsewhere, but for us it's really just one example, hoping to make an impression. I'm not sure if it's very interesting, but since I have a couple minutes, I thought I could at least explain what the first 2 or 3 steps look like, and then I'll just wave my hands and say, oh, the rest is a bunch of calculations. But at least you'll be able to see a little bit where 4-wise independence comes in. Okay? So the suggestion was this thing is a lot like Markov's inequality. And I only want to make that particular point because it's true of other things like Chernoff and stuff as well. Okay? So you start with this term, the probability that's greater than 2 times the expected value. And this thing is at most, you do 2 things. First, you throw one of the averages on the other side. Okay. Like this kind of thing. Okay. But the other thing you do is you amplify both sides. So in this particular case, because it's 4-wise independence, what you want to do is take it to the 4th power. If you're doing something like Chernoff's inequality, you're going to exponentiate both sides. Okay? So left-hand side is bigger than the right, only if to the 4th power it's bigger than the right. Okay? And then what? And then you apply Markov's inequality. So this is the general recipe for a whole family of concentration inequalities, like Chernoff stuff, all this central limit theorem, law of large numbers, analyzing the normal distribution. Okay? And what happens is that this will break up into a polynomial of degree 4, and every time you have like x1, x2, x3, x4, because they're all independent, it sort of disappears. And the only terms that are left are things like x1 to the 4th, or x1 squared, x2 squared, so forth. So from there, it's mostly calculations. Okay? But I think all I really wanted to point out is that there's one step of sort of amplifying, so to speak, both sides. Okay? And then the next step is ultimately applying Markov's inequality. Okay, so you're sort of analyzing the random variable formed from some function that sort of ramps up large deviation.
Okay,
right? Because
I found this on the web for we are sort of analyzing the random variable formed from some function. Check it out.
I have no control. So at some level, if you look at x1 plus xn minus mu to the 4, if that's a very big number, to the 4th makes it bigger. That's bad. But if there's a small number, to the 4th makes it smaller. And that's good. So that's why you amplify it before applying Markov's. Okay, that's all. Sort of boring, but thank you.